Okay. So we, as usual, continue looking at the exam questions, just as we promised the house that we need to do these things this year as quick as we can. And the question number that we are looking at, interesting enough, we want to consider question number 2. I know there is a lot of work that has to be done, but I'll be able to explain and make everything clear. Let's pick question number 2 for this conversation. Do I have anyone confirming if you can hear me? Can you see the screen? Are you able to see the screen? Can you hear me?
Yes.
Anyone to confirm if you can see the screen and you can also hear me?
Yeah, we can see it and we can hear you.
Oh, thank you for the confirmation. Thank you. All right. So now, this is the question that we have. And it is reading that the following non-linear demand function is for, television sets in Lusaka. So the first question is to transform the demand function into the logarithmic form, into the log form. Okay. The function is a non-linear demand function. So you have to make it linear and introduce the logarithmic functions. Yeah. So maybe to pick some ideas to the people, how do you transform a matrix? How do you transform a demand function that is non-linear and make it linear? Do you remember something like this from business statistics? That's business mathematics. You remember the exponential function and the log functions, something like that, the logarithmic functions. I'm guessing there are a few people that are able to remember the log functions. But how do you transform a function? Okay. According to the law of the logarithmic function, let me start from here. What it means when we say a function is non-linear, that simply means the function has the coefficients, because these are coefficients. The coefficients of a function are raised as, the coefficients of the function, they are raised as the exponents. So when you have such a function is a non-linear function. Or you can have an example of a Cobb-Douglas function where you are given that y is equal to, let's say you have got, the constant a capital raised to the power, let's call it alpha, times labor raised to the power beta. You see, this function is a non-linear function. Why? Because these are coefficients. If you look at, these are coefficients. The variables that you are looking at actually are variables like capital, they are variables like labor. So these are the variables that we are looking at. But when you look at alpha and beta, these are the coefficients. So the coefficients are raised as the exponents or as the powers. So how can we transform such a function into a linear so that the idea is to make sure that these exponents, they come down in the line, it becomes a linear function. So that's what you do. So it's very easy. That's why it's even 1 mark. So what you do, you introduce the logarithmic functions on both sides. You can introduce even the natural log or a normal log that you know. Let's introduce the log of the quantity demanded, okay, quantity superscript d that's demanded of good x. That should be equal to the log, okay, the log of what? The log of px to the power 0.4x, okay, plus the log of p lower script subscript y to the power 2.5 plus the log of of what? The log of m to the power 0.2. So what rule did we use here? There is actually a rule of the logarithmic functions that says that if you're given a logarithmic function that is, let's say y is equal to a, b, c. This is same as, log y should be equal to the log of, a plus the log of b plus the log of c. There is this rule of the logarithmic function. It actually says that where it's possible for you, if at all, sometimes you can be given a logarithmic function like this one. Okay, let's say we have a log function like this one. It's already logged both sides. We have log y, that is equal to log a plus log what? Log b plus log c. So we want to transform this into nonlinear. Here it is already linear, okay? We have to make it non-linear. So if you're asked to make it non-linear demand function, you make it non-linear. What you can just do, according to the rule of log functions, show that you can, say you have log to the base e y equal to, just pick one log here. Okay, since they all have the logs of the same bases, you can say log, then to the power. Lift up these as the powers, a, b, c. The log of the power a times b times what? C, like that. Still the same thing. So that log and log can do what? Can cancel. And again, your function will be y is equal to what? A, b, c, like that. That will be your function. So again, if you want again, you can still transform this log again and again. Okay. Going back now to our question. So I was just reminding you where this whole idea of logging both sides comes from. So just introduce a natural log everywhere. And as you introduce the natural logs, you will see that you introduce a plus sign, because a positive sign, plus, goes with multiplication when you're dealing with the logarithmic functions or with the log functions. So from here, what you can do actually, according to the rules of the logs, there is a part in logs that there is a rule that says if you have a log, let's say a function y, and that is equal to log what? Log x to the power b. This can still be rewritten as y is equal to b log what? Log x. This is what it means. You can drop the power as a coefficient, then log to the variable. So far up to here, are we together? Anyone with a question? You can ask your question. Hello, do we have any question?
Maybe you just do a recap. I've not yet connected.
You haven't yet connected. It is well. So I was saying that what you can do, because the question is asking you to transform this nonlinear demand function into actually a logarithmic form. So in short, it should have the logs. You can decide to use these log that are best, or you can use the natural logs. Okay, still the same thing. All of them are logarithmic functions. So what you do, you introduce a logarithmic function both sides on the left side of the equation. And once you introduce a log, for example, you can say the natural log of q, that is equal to the natural log ln of p x to the power 0.4 plus again the natural log of p y to the power 2.5 plus the natural log of what? M to the power 0.2. So in short, to transform this first thing into linear, you have to introduce the logs everywhere. And and make sure that these logs, you are introducing a plus sign everywhere. Why are we introducing a plus sign everywhere? Because we can manage again to rewrite this same equation. If you want to take it back to where we found it, it's very easy because you can just introduce a natural log, of course, the natural log of Q, that is equal to, since here natural log is common on both sides, like on the right side, natural log is common. You can get the natural log, and then these can be now raised as the powers, okay? Natural log, or then you say, you open the bracket, P x to the power 0.4 times P y to the power 2.5 times what? Times again, M to the power 0.2. So that natural log and natural log can cancel. Why? Because the natural log that is base the n is as good as 1. So it's just 1. So like this is just 1 ln to the power to the base e, as long as the base here that is there, or there is no base that you are seeing, just know that there is base e according to the rule of the logarithmic functions. So if you don't have any base I, you don't have any base of the log, of course the natural log, just know that there is 1 there. It's just as good as base e. Now the natural log of base e is 1, like it's 1. So it's just as good as there is 1 here, like the whole lot of this is 1. 1 times Q, meaning Q. Even here, where there's natural log is 1. 1 times everything, then it would go back to this one. You got it? Don't worry about the log functions. So in short, we have said, can you just log all of them? Like log the letters and put a plus. Yeah, maybe the summary of it. Just log everywhere. Okay. You can introduce the logarithmic function everywhere, like left and right side. Log all the variables, okay, so that you can produce a log model, like a log to log model. So just log both sides. Log on the log on the dependent variable, and log on the independent variable.
The one
Sorry?
we did on the one we added on the ABC, we put together, we just
exactly. So like the way how we did even just on the ABC, you saw that good example, that example of ABC that I gave you. I say that if you are given the function, let's say Q is equal to A, okay, let me write like this. Is equal to P to the power B, right? B, A, not B, to the power A, okay? And we have got, let's say, maybe Y to the power B, or if you want, you can put W to the power C, right? So you are to log these. If you are to log all of them, you can just say log of Q is equal to the log of P to the power A, follow nicely, plus the log of Y to the power B, plus the log of W to the power C. Why are you saying that? It's because since the log is common, right? If you want again to go back, like from here, if you want to go back to this, we know that log is common on the right side. We can just pick only one log and add the powers. Okay? Like log is common. Yeah, on the right side. Check that log. Everywhere there is log. Yeah, so you can factor out the log. And once you factor out the log, then you can multiply these these powers that you have. Okay. So once you log everywhere, let's factor out the log. So you can say log Q is equal to, get the log outside. Then what you remain is just, you just remain with these that you can manage to do what? To multiply. Like, so it's just the same message that we are communicating. You got it?
Yeah.
Okay. So in short, when you are logging a non-linear function, just introduce logs everywhere. Right? Log both the dependent variable and all the independent variables. You remember regression analysis in statistics, we said these that sit on the right side, we call them the independent variables, right? They are the independent variables, and then this one is called the dependent variable. So like you log both sides, log the independent variable and also the dependent variables, like log everything. That's the first step. You got it? Nothing much. Log and say plus. Log even here, put plus, then log. And once you log all of them, now look at what is happening here. There is a rule that I introduced to you of the log functions that says that if you have a log like this, let's say you have a log x to the power b, right? You can still rewrite this as y is equal to b, where you drop this power, right? B log x, okay? There, you can still rewrite this, they are equal. It's just one of the rules of the logarithmic functions. That's what it states. Have you gotten this rule first before I go to the next step?
Yes.
Right. Anyone with a question? Okay. So if you've gotten that, then it becomes a bit easier now. So what you can do for that reason, then we can say we have the log of q, dx, that is equal to, let's drop the power from what I've said. So 0.4 log what? Log p x
What?
plus 2.5 log what? Log p lower script y plus 0.2 m. Oh, 0.2 log m.
Log m.
Yeah, 0.2 log m anyways. If you don't want to introduce these logs, you can introduce ln, which is the natural log. You can even introduce the natural logs. It's still okay. Like it's still a log function. So this is where I end from, like for the first part. Like this is now a logarithmic function, okay? It has been transformed into a log form. Did you get it?
So that's question 1 all about.
Yeah, that's A1. Now we have converted it.
Adding log to the equation here.
Yes, so we are transforming it into the log model. Remember, it wasn't a log model, this one, it was a non-linear demand function. So we are making it linear, and by making it a log model. So a log to log model has been produced, and this is how it comes out. So you've seen that all these exponents have dropped down as they are no longer powers, but they have become coefficients. You got it? It's not even complicated. So now, sometimes you may be given a log model like this, then you are asked to transform it into non-linear, you have to make it take it back to non-linear demand function. How would you go about this now? Follow nicely and see how we get back to where we came from. Don't worry, I'm not rushing to answer the question. I want to make people understand. So what you can do is that you can start by number 1, the next step, you log q, dx equals to, take these, the first step is take these back to being the powers, because you remember that rule that I told you where y is equal to a log x is equal to b, can be converted as y equal to what? B log x, this one. So you can take these back to the powers, like where you got them from. They can be powers one more time. So you have to have a log of what? px raised to the power 0.4, plus the log of py raised to the power 2.5, plus the log of what? The log of m raised to the degree 0.2. That's the second step. Then from there, you and I know now that since all of these are raised to the power log b, then you can multiply all these that remains as you factor out the log. Okay, this side. It's very easy. You can just factor out the log here on the right side. Say we have log. We have a log, open, then we have px to the power 0.4, right? Times p, okay, y to the power 2.5, times, m to the power 0.2. You close like that, log q g. Then you divide through by the log on both sides so that log and log does what? It cancels. You've seen that now it has gone back to a non-linear, right? Hello?
Yes, sir.
I'm hoping that I'm simplifying issues. I'm not even complicating anything, isn't it? Like we are trying to make everything simple and straightforward for all of us. So please get used of the different forms of the functions, yeah? Because the lecturer may want to be very interesting. There are different forms of functions that you should actually be introduced to. Not that you should be, that you were introduced to in business mathematics, since you did it already. Like you can be given an exponential function, okay? You can even be given an exponential demand function, exponential functions. You can be given a log function like this one, a logarithmic function. You can also be given a trigonometric function if you want to be more interesting. A trigonometric function, yama trig, those sine what? You say you have got, sine x raised to the power 2, all these, yeah, tangent plus secant, those are trigonometric functions, okay? So be conversant with the different forms of the functions. I do not think they can introduce the Cobb-Douglas function in here, but in case it does come, you can still manage to handle it. It's not very difficult. I'll look for questions that have got these other forms of functions, right? Where you can be given maybe a trig function. I'll try to look for the questions where you can have a trig function, a Cobb-Douglas function, a Cobb-Douglas production function, and just these other forms of function, including the exponential ones. So we'll look for them, then we'll bring them here for discussion. Okay? All right. So now let's go to B. Part B is saying, what is the price elasticity of demand and the cross price elasticity of demand? So now, first of all, we need the linear one, because we cannot start finding the elasticity of demand. The elasticity of demand is found by doing the derivatives. So we have to make it linear. The way how it is here, the function, the way how it is, you cannot manage to apply the derivatives. The derivatives, you can't differentiate here. So you have to make it linear. Let's go back to the way how it was. We had made it as log what? Log Q, whatever, equals to 0.4 log px. See what they said? Yes. Plus 2.5 and log p of y plus 0.2 and log of m, right? This is what we got when you transform the equation. So this one is a linear function. It's a linear defined function. So we can manage to find the price elasticity of demand. How can you find the price elasticity of demand of this linear logarithmic function? Any idea? This is the on price elasticity of demand. How do you find it? Hello? But are you able to get me, right?
Yes, sir.
Okay. So now, observe that the good that we are dealing with is called what? Good X. So if you're looking for the on price elasticity of demand, it means that if it's a linear function like this one, the way how it is, you have to derive it, okay? You have to derive it with respect to P of X, the price of good X, okay? You have to differentiate the function. Differentiate the function and get these the marginal effects. What is happening is that, let me, Basa, be more clear. You don't sound to be very clear. Try to make everything simple. What is there is the way how we interpret these equations, right? The elasticity of demand. When you're using a linear demand function, like the one that deals with the units, where you don't have logs, where you don't have any log, right? It's not a logged model. You use the units to interpret the changes. But for this one, where you have where the model is logged, right? Where the model is a log to log model. So if you're using a log to log model, you use the percentages, like you use the percentages, and these are basically the marginal effects. We call them the marginal effects, which is still the elasticity of demand, but you just call it marginal effect. Why? Because of what? Because of the logs that have been introduced all over. So it's still just one and the same. So how do you find the price elasticity, the on price elasticity of demand of this function? You differentiate this function with respect to price of y, okay? The rest of these that don't have price of x, the rest of these that don't have x, okay, they are going to be treated as constants, isn't it? You will treat these as constants. And you know that all the derivatives of constants are zeros, right? Do you remember? I think last time we had something similar to this in managerial economics, where we were saying that if you differentiate, you do the from differential calculus. If you differentiate the non-linear, the constant, you get a zero. Those are the derivatives. So let's treat these as constants. So they are zeros. So the only part of the equation that has remained is log of quantity of good x that is equal to 0.4 and log of the price of good x. So we have to differentiate this logarithmic function. Okay. So how do we differentiate the logarithmic function like this one in this case? Do you remember something about how to differentiate the log functions? The derivatives of how to differentiate the logarithmic functions. You don't remember? Okay, it's okay. Don't worry if you can't remember how to differentiate the log functions. I think years have passed, many years have passed from mathematics. But according to the rules of differentiation, differential calculus, if you are differentiating a function like this one, a logged function like this, logged from everywhere, it will just give you the constant like this. That's how to summarize everything. Now I'm simplifying everything that I don't want to be more technical. You get the constant. So the derivative of this whole function, like the log q over the log, the log of px is equal to the coefficient of the function, which is actually 0.4. Those are the rules of the logarithmic functions that were covered in business mathematics. So it's okay. So that's what is there. You get the constant in short, as simple as that. So this is the price elasticity of demand, the only price elasticity of demand. We've seen it is 0.4. Maybe an additional question would be, is this in elastic, price inelastic or elastic? What do you think? Is this elastic or sorry?
Elastic.
It is elastic, right? What about others? What do you think?
I feel also it's elastic.
Okay. When does it become inelastic? When does the demand sun become inelastic? Maybe I should ask like that, so that we help.
When it gives us a negative.
When it gives us the negative. What if you get a 0? Exactly. What if it gives us a 0?
Perfect inelastic.
It is perfect inelastic. What if the answer is equal to 1? To positive 1.
So if it's less than 1, like 0.0 any number, then it's the inelastic.
So you mean like this one is inelastic?
Yes. Then when it's greater than 1, then it's elastic.
Okay, it's elastic. What if it's equal to 1?
When it's equal to 1, then it's what we call it, unitary elastic. That's when
It's unitary. It's unitary elastic.
Yes.
Okay. Then 0.
Then 0 is perfectly inelastic.
Perfect inelastic. Greater than 1.
Then it's inelastic.
Okay. All right. Thank you very much for that one.
Greater than 1 is elastic. Sorry.
Yeah. Greater than 1 is elastic. But what if it's equal to positive infinity? What if it's equal to positive infinity? All right. We will be fine. Don't worry. No one should get worried. We are fine. Now, listen carefully. When you're dealing with let me start from Mr. Shakasungu. You are very much right. That one applies to, you don't, if you have not taken the absolute terms, it's possible when you are dealing with a linear to linear log or level to level model. You get it, eh? You can use that one, that approach where you are looking at the numbers that are just ranging between 0 going to -1 and to +1, because that was the approach you were using. So that one is only used for a level to level model, not for the logarithmic function. You know, the logs do not, like you can never get an answer of a negative log. Let me put it like this. The logs never support the negatives. You got it? So what you do, you look at things now in absolute terms. So they should just be between 0, 1, and above 0. nothing less than 0. Did you get it?
Yes.
Yes. So instead of looking at it from dealing with those values, get the absolute values. Why should you get the absolute values? Because the log functions never support negatives. If you want to, you can if you plug into the negative numbers into the logarithmic functions, it doesn't come out. It's undefined. Okay, so that's it. So would head that same direction. So for that reason, just as said, whenever you get the answer between 0 and 1, but not equal to 0, not equal to 1, it is inelastic, okay? Inelastic. But when you get the answer equal to 1, that is unitary, elastic. If the answer is greater than 1, that is elastic. But if the answer is positive infinite, that is perfectly elastic. Perfectly elastic. And if the answer is equal to 0, that is perfectly inelastic. Do you remember those things? That's always a bit of microeconomics, I think, now. Are we okay? Do we have any question up to here? Okay. Let's go ahead. Are you able to hear me, Bart? Are you able to hear me?
Yes, yes, I can hear you.
Okay. Let's have point C where we ask. Oh, we haven't covered the other part of the question. Sorry. There is also the part for cross elasticity. What do you think we can do when you're dealing with the cross elasticity of demand? The cross price.
I think the P over the power 0.4, we consider it as a constant.
Yes, this one is a constant 0.
M to the power 0.2, also consider it as a constant. We remain with the
Okay.
y function.
Okay, so the function that will remain with the q, x equal to 2.5 log py, like that, of which from what we have just said is 2.5. So now, since the cross price elasticity of demand is 2.5, obviously we have already interpreted this is whether it's now my question is, for cross price elasticity, are these substitute goods or what are the other ones? Substitute or what? What's the other one? That other one. Substitute goes with what? Complements, right? Substitute goes or complement. Based on the elasticity that you found, are these substitute goods, good X or and Y? Are they substitute or complements? Hello? Are these substitute goods or complement goods?
They are substitutes because they are the positive number.
All right. So as long as the marginal effect is positive, or the price elasticity is positive, they are substitute goods. If it were negative, it was possible, by the way, you find other logs, the other functions where these powers are negatives, okay? If this power is a negative, when you drop it, it will be maybe negative 0.2 log something, log a certain number here. You get. So now, if you get like a negative number like that one, for example, this one. If you get the exponent that is negative, then that simply means that you can, those are what's this? The complement goods. Okay. Go ahead and have another question. Would you consider televisions to be normal goods? And explain. How can we decide whether these are normal goods or what is this? Inferior goods. What criteria would we use? How are we going to decide whether these are normal goods?
We are now going to consider the income.
Okay. So we take the derivative with respect to income, isn't it? Log Q is equal to 0.2 positive and log what? The log of M, right? So obviously the marginal effect is 0.2 positive. And is this a normal good or an inferior good? Is it an inferior good or a normal good? Hello? Is this an inferior good or a normal good? Okay. So this is said to be a normal good, yeah, because of course the the marginal effect is 20%, is positive. Okay. I told you these are percentages. We interpret them in terms of the percentages. So this simply means 1% change in what is M? In income can lead to 20% change in what? In quantity of what? X demanded. Is that clear? Like that's the interpretation would be 1% change in income leads to 20% change in what's this quantity demanded of good X. You got it?
Yes.
Okay. So basically, that's how to. So how would you? How would a 20% increase in income affect the demand? We have already explained how it affects demand. Demand increases, right? If you change income, demand does what? Increases. Why should demand increase? Because these are normal goods, as we have already established. So, ndio so.